Alright, so today I'm going to be explaining another important article with the title Total Variation Graph Neural Networks. So again, another good article from Bianchi, the guy who talked about mean cut and introduced several interesting hierarchical graph pooling. So this time he wrote an article in ICML 2023. Recently proposed graph neural networks for vertex clustering are trained with an unsupervised minimum cut objective, approximated by spectral clustering relaxation. However, the spectral clustering is loose. This relaxation is loose. And while it offers a closed form solution, it also yields overly smooth cluster assignments that poorly separate the vertices. So we propose a GNN model that computes cluster assignments by optimizing a tighter relaxation of mean cut based on graph total variation. The cluster assignments can be used directly to perform vertex clustering or to implement graph pooling in a graph classification framework. Our model consists of two core components: a message passing layer that minimizes the L1 distance in the features of adjacent vertices, which is key to achieving sharp transitions between clusters. Yes, this L1 distance creates it sharp. The second one is an unsupervised loss function that minimizes this graph total variation of the cluster assignments while ensuring balanced partitions. So you see, most clustering methods partition the data only based on the features. And spectral clustering partitions the vertices based on topology. So GNNs account both for vertex features and graph topology. And in B, you will see the difference between smooth and sharp cluster assignments. Especially at the edge of a cluster, the smooth assignments give large weights to more than one cluster. So the task of finding K clusters of similar size can be cast into the balanced K-cut problem, which is just a ratio of two set functions. The numerator, if you look at the numerator, this cut of two clusters, the numerator can be expressed as Z transpose LZ. And Z could be any value, just two value, is a -1 or 1. The common relaxation done in spectral clustering is this one. We say, instead of taking the discrete values, just -1 and 1, we take it to be in Rn. So instead of vectors of 1, -1, 1, 1, -1 in Rn, in Zn, we take it to be, it could be continuous as well. For example, it could be something like this. And so this is in Rn. This is a continuous relaxation. So what a C relaxation actually does is to apply Laplacian smoothing to graph signal by minimizing local quadratic variation. From the graph signal processing perspective, Laplacian smoothing applies to a graph signal a low-pass filter with response 1 minus lambda I. Lambda I is the ith eigenvalue of the Laplacian. Despite offering a closed-form solution, spectral clustering gives a loose approximation of the solution of discretized optimization. So let S sub k be soft assignment vector for the case cluster. A tighter continuous relaxation of the asymmetric Cheeger-Cut problem is by giving this objective. So in the numerator you will see is GTV, which is called graph total variation. GTV, this term, measures the graph total variation of the soft assignments to cluster K. And in the denominator, quant denotes the row quantile, the Q plus 1's largest value in S sub K. So differently from C, this equation, this asymmetric Cheeger-Cut problem minimizes the L1 rather than L2 distance. As you see, this is L1. Here is L1. But here is L2. So here is L1, that's why it's sharper. That's it. The idea of this paper is this. Rather than the L2 distance between the components of S that are adjacent of graph. Minimizing graph total variation yields sharper cluster assignments and achieves a tighter relaxation of the balanced K-cut problem compared to what we do in spectral clustering. However, contrarily to spectral clustering, it is non-convex. So this one is very convex, good solution, global solution, but this is non-convex. This is the drawback of this new approach. So it's a little bit. So to leverage the graph topology for learning vertex representation, GNN implement message passing layers. Typically, the message passing layer collects information from neighbors to update the representations of each vertex. So an example of message passing layer is graph convolution, AX theta. You know, A is just adjacency, X is the hidden value, and theta are the parameters, learnable parameters. So the else GCN update of the vertex is this, which is actually one gradient descent step of size delta in the optimization. So after applying L message passing layer, the soft assignment is obtained. For instance, a mean cut pool, if you remember, I explained this in a different video. If you remember, that optimizes this following loss, where the term L sub C encourages strongly connected components to be clustered together, while this L sub O is just a balancing term that promotes equally sized clusters and helps to avoid degenerate solution. Similarly, DMON optimizes a two-termed loss, where D is degree vector, L sub m pushes strongly connected components to the same cluster, and L sub r is this one is just a regularization term that penalizes the degenerate solution. The losses in 10 and 11 are closely related to spectral clustering, from which the problem of smooth cluster assignments is inherited. In addition, being trained with gradient descent, the graph neural networks do not exploit the closed form solution of spectral clustering. This motivates relying on graph total variation to perform a clustering with GNN. So first we define the graph total variation. As I said, it's just L1 norm. Then we define the symmetric norm term. Now, to control the range of values of the loss, the two terms are rescaled. So both of them are rescaled. And E here, if you look at E, is just the number of edges in the graph. And beta here is this term. And now we add the graph total variation and AN. This AN. Finally, the cluster assignments are computed by a multi-layer perceptron, just like previous methods. So our goal is to design a message passing layer that minimizes the graph total variation. While the graph total variation can be expressed by means of an incidence matrix, L1 Laplacian operator, these formulations are difficult to integrate with a standard message passing layer that operates on a connectivity matrix. To address these issues, we define graph total variation Laplacian as this one. So gamma is connectivity matrix matching the sparsity pattern of adjacency matrix with these elements. So to minimize the graph total variation, we compute the partial derivative of x with respect to vertex k. So take the derivative with respect to x. So the full graph total variation is this one. So by looking at 21, we now see that the constant epsilon ensures numerical stability by avoiding the discontinuity in the derivative of x. So the aggregation procedure that we do here is only valid for univariate vertex features. For graph with multivariate, multidimensional features, the partial derivative is this. So we modify the gradient descent step by defining a single operator that computes the L1 distance over the full feature vectors. By referring to the notation 7, the proposed graph total variation convolution is just this. This is the update equation. And L sub t is just this one. And you can cascade it, multi-layer perceptron pooling, convolution, MLP, again pooling, to get the cross entropy loss, and then by backpropagation you get the weights of your variable. And they did some experiments on, for example, PubMed. Of course, this is the highest average of ACC and NMI for vertex clustering. But the graph classification nowadays is too high. For example, for Colab, it's still 79 in this paper. So it's in this paper is 79.8. So almost the same, mean cut pull, demand. You see, you don't see any sensitivity. If you do sensitivity analysis, you will understand that they are in the noise, all of them. You cannot differentiate these methods too much.